Hello, welcome to this section on interprocess communications in the operating system. Now, this is very popularly called as IPC, interprocess communication. Now, let us first understand why do we need it and what do we achieve by having these features in the OS, or the OS supports the IPC mechanism. There are many which we will cover as a part of this particular section. Now, as we know, in a system, a CPU is there. It could be a single CPU or a single core processor, or you may have a multi-core processor. Now, and it accesses the memory, which I am assuming that it is in the main memory, the program code, whatever a process needs, they are all there in the main memory. Now, I am not bringing about any internal cache here. Imagine an operating system is there as a part of this in the main memory itself, which is helping us to create multiple processes. Now, when we say that we have already learned about a process which is a single sequence of instructions, a instance of execution, this is a process. Now, there may be a thread which is created by a process, which also could be a single instance of execution. Now, you may have a thread created by a process, or you may have multiple processes running in the system. There could be different users running, user processes, user 1 and 2 are running different processes, and kernel is also running different processes. Kernel processes are there. Only difference is the kernel processes run in the kernel mode and user processes are in the user mode. Now, kernel processes have a different access permissions which happen to be in the kernel mode, so they are allowed to access any part of the memory, or they are allowed to execute some instructions which are not allowed to be executed in the user processes. These are all fine. Now the question is, when we have multiple processes running in the system, do they have to communicate with each other or not, or they can they run independently? The answer is yes or no. If there are two processes belonging to user 1 and user 2, we don't expect them to be talking to each other. In fact, they don't even know that the another user is there in the system. You sharing the CPU, sharing the memory, and of course, the OS is providing access to the CPU as well as the memory without the other processes be kept in the loop. In the sense, they are not aware of each other, the existence of each other. Imagine a situation where you have a big Unix server or a Linux server where multiple users are logging into the system. They all get their own directory structure, their own spot of the hard disk, and their processes run in the system. They all coexist in the CPU. So there is no need for them to talk to each other in case they are all running independent processes. And in fact, they are not even aware that other processes run, and they share the CPU or they share the memory where other processes are also there in the system. But the IPC mechanisms come into play, which is interprocess communication, where we have cooperating processes. That means they all cooperate with each other. That means for them to do some job, not only that they need to execute their own piece of code, they also need to exchange some information or be in sync with what is happening in the other processes. Now, if they need to do, they need to depend on OS to provide the inter-process communication. That's what we are going to talk about. That means they want to exchange some information, or they want to know what is happening on the other process, or they want to know, maybe I have completed up to this point, I want to wait till the other processes comes to some other state, then I will continue with the other thing. So they need to be dependent on what is happening on the other process. Now, is it not very easy for a process to know what is happening on the other side or in some other process without the help of OS? Why should the OS be involved? The reason is, as such, as I told, the CPU, memory, and any IO devices like even keyboard or display, they are all shared resources between multiple processes. When you have a Windows system with PowerPoint running, PDF running, and even this video recording is running in the background for me, all these are all individual processes running, and they all share. In fact, the screen what you see is being shared by this particular whiteboard application up to this point. But when I come here, it is the desktop, which is maybe I can keep another PowerPoint here or a text document here, which will be a part of the display will be shared by that particular process. So whatever is happening, or YouTube is playing in the background, whatever is happening in that window is being displayed on the screen, whereas what I write here is being displayed on the this part of the screen. So this application is sharing this display itself. So not only that they are sharing the CPU, not only that they are sharing the memory, even the IO devices they share. Now all these are all controlled by the OS, and they need to be in the loop for even sharing the IO devices or sharing the memory or sharing the CPU. Now why do I say that a process which is running here will not be aware of other processes? Because they are defined or designed to be like that. Because we don't want a process getting interrupted or getting disturbed or corrupted by another process which is not a cooperating process, or which is a process belonging to some other user. But when you want to use the same system wherein multiple processes need to cooperate, then they need to have a mechanism from the OS to exchange information, and then even synchronize between their activities. We need the support of OS, which is the topic of discussion in this series of videos that we are going to be learning about. Now, let me just quickly go into different mechanisms that are supported by the OS. Then we'll quickly see what are those features or what they support. Now, what are the different IPC mechanisms? Interprocess communication mechanisms. These are various types of IPC mechanisms supported by OS to enable processes to share data among themselves, because naturally they are all defined to be independent and they are expected to be protected against each other. In case if you want to relax a situation wherein multiple cooperating processes need to share some part of the data, not everything, then we need to get the support of OS. That's what is the job of this IPC mechanisms provided by the OS. Now, shared memory is one way of doing it. We will see it shortly about what it is. Maybe I will give a short introduction about that. I said that we are sharing the main memory, correct? We have multiple processes running. Now, when I say they are sharing, physically this main memory is being shared by this process as well as this process. That means physical memory is there, 4 GB or 8 GB what you have. Some part of it is being used by this P1, and this some part of this memory is being used by P2. They are sharing this physical memory. That doesn't mean that they can look into each other's memory or each other's data. They are not allowed to do it. But if I consciously say I want this to be allowed, then I need to have a mechanism that as some part of this main memory, I will say that it is a shared memory. Then this can be accessed by P1 as well as P2. Then this is with the help of OS. I can say that some part of the memory can be shared. So do not get confused between P1 and P2 sharing the main memory. That is, they are running on the same main memory. So I am saying they are sharing from the physical perspective, but they don't have access to each other, where they are two different independent processes. I am not talking about threads running in the context of process. I am now talking about two different processes. They share the main memory. That is, some part of the main memory used by P1, some part of it is being used by P2. P1 does not can read the memory of P2. P2 can also cannot read the part of P1. But in case if you want to consciously allow some part of the main memory to be shared between P1 and P2, then there is a mechanism called shared memory. Now, what is message passing? Now, if suppose you want two processes are there, P1 and P2, they have something to be shared or sent across. It's like sending a mail from one user to other user. So within the same process, they cannot just like that share some data. Shared memory is one way of doing, because I said that some part of the main memory is allowed to be seen by both of them. That's one way of doing it. But if you don't do this, if I don't have this feature, I can actually use the message passing feature, wherein I bundle some data, maybe 10 bytes, 100 bytes, 200 bytes, and send that data across to P2. That is called message passing. Pipes. Pipes is one way of, you would have seen that Linux command. I say cat, then I pass a pipe, and then maybe I will do a ls, then I pass this to this, and it can go across, right? This is like a stream where a data is put on one end of the pipe and it appears on the other end of the pipe. So in Linux command prompt, we use this symbol for showing the pipe between two processes or multiple processes. Now, Semaphore and Mutex will come to this soon, okay, as a part of this discussion. Is one mechanism wherein you want a piece of code to be executed only one at a time, or piece of data area, if you want to access only one process at a time, then we use Semaphore. Signals, control C is one good example, wherein you want to send some signal based on some input or based on some time or keyboard entry, then signals or events or timers, if it is running, then it's also an event. Okay, that's one way of communicating between multiple processes. Condition variable, we are not talking about this in this system. Barriers is something like, suppose you series of players are there, they are participating in a running competition, then when you say set go, and we say that all of them can start off at a particular time, then it's called barrier, wherein we want to wait for all the processes to come to a particular stage before anybody proceeds further. That's called barriers. Okay. Spin lock is another mechanism. We'll come to that soon. Network socket is something between two different machines or over the network. We want to communicate something. We send data across. That is network socket. So these are all different mechanisms provided by the OS for sharing some information. It could be actual data, or it could be a simple event, or some small packet of data which is being sent across between processes. So various uses of IPC mechanisms: sharing of data between concurrent processes, we use shared memory; notifying some event has happened, we use semaphores. There is no associated data here. We only say some event has happened. It doesn't communicate what is that event, what all the associated information. Nothing is sent. Okay. Sharing continuous stream of data. We use pipe between two processes in the system. If it is across the machine over the network, then we use network sockets. Then providing exclusive access to resources. Suppose you have a printer, multiple processes, multiple users are trying to print something. We allow one user at a time, so that that particular print job is completed before some other user job is taken up. Controlling a set of processes with a single event, that's barriers. You want all the processes to come to one particular known state, then before proceeding further. Message queue, we want not only to communicate that some event has happened, we also have an associated data to be shared between two processes. We use message queues. Controlled access provided is spin lock is another mechanism which is purely done in hardware, where a semaphore is hardware, support is there, but it is implemented in software. So semaphore and spin locks are synonymous, but implemented in a different way, and their behavior is different. We'll come to that. Network circuit, I already told you. So why do we need interprocess communication? Explicit interprocess interactions. Why? There are three primary forms of interprocess interactions. Let us understand three of them. Okay, quickly: interprocess synchronization, signaling, and communication. Now, synchronization means there are set of protocols. Suppose you have a shared data which cannot be accessed by multiple processes simultaneously. Okay, you want one process at a time to be using that particular data, because whenever any data is accessed, suppose it is being modified, the data is read from the memory and taken to the CPU, and it is modified and returned back to the memory. During this time, another process is reading the same data. It will get a different value, and if it is also parallelly updating it and putting it back, we might miss in between some update done by the one of the processes running on the system. It could be on the same CPU or on a multiple multi-core processes environment. So we need to have a mechanism where synchronization is achieved and only one process does the job at a time. So this is a good example of this interprocess synchronization when concurrent processes share the resources. When I say resources, it could be a database, or it could be a hardware like a printer, or it can be even a small linked list update happens should be happening one process at a time. So it is serially reusable. That means you can use the data, or you can keep adding a node to a multiple nodes to a doubly linked list, but only one node should be added at a time. Otherwise, you will have a problem of updating the previous and next pointers in the node, and multiple processes manipulating the linked list simultaneously will lead into linked list broken up, and you will not be able to even get the data which is in the linked list. So it can be completely gone. So you need to make sure that linked list is updated one process at a time. So that for that you need some mechanisms, which is Semaphore or Mutex or spin lock is one method of achieving this, and we'll learn more about each of them. This is only an introductory lecture about inter-process communication. Now, what is signaling? As I told you, if I am pressing a Control C, I need to inform that okay, the user is interested in stopping the process. That signal has to be informed or communicated to the process. So that's one way of IPC. Whereas there is no associated data, it only says that user has pressed a Control C, the process needs to be stopped. Or there could be a timing interrupt which is coming from the timer. So this this is one way of signaling. Another one signaling is, suppose two processes are running. Suppose you have a mechanism dependency on one process that it should complete up to this point, and then it should inform the other process which should wait for this completion to happen before proceeding further. Now imagine two processes are there, they are running in parallel and they are independent of each other, but they have a dependency that this process should have come to this stage before this process proceeds further. It could be that up to this point, maybe a data is updated, and from this point, maybe this data is needed for this process to continue. Suppose a good example is, suppose I am decompressing some image and then putting it in a main memory somewhere, and then it is going to convert that image into some other format. Now decompression of that particular image file should have been completed before I take up to do a decoding or encoding of this information or translating it into one format. If I do it in halfway through, this file may be in a intermediate stage where it is getting updated, the intended work will not be done. So there will be a synchronization between them, between two different processes. That is signaling is one way of saying that I have completed this much, you please proceed from there. Okay. So real life example is set of friends planning going for a trip. Suppose they are all coming to a bus stand and then they need to get into a bus. Unless everybody reaches the bus stand, nobody should get into the bus. If that is the case, then every friend who is coming from their individual houses and reaching the bus station should communicate to the people who are in the bus stand to make sure that they all get into the bus only when all of them reach. But they're all coming from different point, and the time they take to reach the bus stand will be different. It depends on what is the time of the day, and then what is the traffic on the way, or whether they are coming by walk or any vehicle they come by, or maybe there may be some dependency that they started late or they are held up because of some on the way some event has happened. So each of them reaching the bus station is independent of each other, because you are imagining that they are all coming from different parts of the city, but all of them need to be there before the event of getting into the bus happens. So this kind of event is one good example of independent processes running on different cores, and then they all wait for some way of communicating between each other so that they know the progress that is made by each of those individual processes. So signaling is one method of communicating that information between processes. Imagine, or please understand that even though the processes are running in the same CPU, they also share the same memory. They don't know the process, each of the processes, how much they have progressed. They are all in the silos. They may be running on multiple cores, or maybe they are sharing a single core, but still they do not know how much of progress is made by other process unless they communicate using this OS IPC mechanisms. And then communication is a way of sharing some data. Message queue is one way of sharing actual information. Not only that I have completed it, this is what is the output of my completion or a process that I have done. So exchanging of data is what is called interprocess communication. Shared memory where you share the actual data, and message queue is one mechanism wherein also you share information between two processes. Okay. So now, to prevent timing errors, concurrent processors must synchronize. Even accessing the shared memory, though two processors or multiple processors may be accessing the shared memory, they need to have a mutual exclusion if they are accessing the same data. If they are accessing different part of the shared memory, no issues. But if they are accessing the same piece of data, they need to be protected against each other, that only one accesses the data at a time. So this is about interprocess communication mechanisms. We will catch up in the next lecture. Bye bye.